All right, I'm really delighted to be here, and I want to actually front load with my acknowledgments. This analysis we're presenting today is made possible by a data set from John Bertram, who we all know from University of Calgary. And I'm really delighted to be here, and also to have brought two undergrads from my lab. The three undergrad co-authors are across the top there. Tudor and Clint are here, and John, as you'll see, contributed to the sort of fledgling wavelet analysis here. With that, get started. And these subjects probably look suspiciously like authors on the paper, but I assure you we were blinded by some sort of Jägermeister last night when we made these videos. So I think having the subjects blinded makes it better. This is just because I had no videos, it's a borrowed data set, and I wanted to give you something to look at and think about walking and running in humans. And most of you probably have a lot more intuitive experience analyzing this than I do. The other point I want to really make clear before I get into this is that the point of this model is to analyze experimental data. It's a very, very general model. It doesn't make any a priori assumption about an inverted pendulum, point mass pendulum, or a sort of idealized slip. So it's something that can be applied to any gait of any animal. And in fact, usually in the past we applied it to quadrupeds, and that's what I reported last year in Jena. And the CF here is abbreviation for collision fraction, which I'll describe today. But this cheetah is taken from a BBC video by Neil Alexander. It's just going through three gaits: the walk, trot, and then switching to the gallop. And what we found from this analysis, we didn't use cheetahs, we used goats and dogs. But we looked at walking, we found a substantial amount of collision reduction. So between a quarter and half of the potential collision was realized, and according to the collision fraction. In trotting, we saw almost the entire potential collision was realized, above 0.9. In galloping, we saw a little bit of collision reduction, so an intermediate collision fraction, about 0.6 to 0.7 of the possible collision was realized. So that's to give you an idea of sort of how general this approach is. It's meant to be applied to any gait of any critter we find. So just a few caveats about what we're doing in this model. It is just a simple point mass model, center mass model that you're all familiar with. They've been used for decades in comparative biomechanics. And it's important to say that point mass model obviously doesn't have any rotations. It doesn't acknowledge that there are any bits that are swinging around relative to the center of mass. And what we're interested in for is its ability to really describe that fundamental interaction between the center mass and the environment on a very basic level. So we do, of course, acknowledge that limbs do work against each other when we have double support, and we include that when we talk about cost of transport later in this analysis. So a few quick definitions. There are three different instantaneous angles that this whole approach is based upon. The first one we call the force angle, theta, and it's simply the deviation of the force vector from a vertical line. And we get this either in 2D or 3D. The concept of an angle from the dot product. We get a 3D angle in that way. The next one is the velocity angle, the other vector we're interested in locomotion, the force vector and the velocity vector. We define the velocity vector as an angle of deviation from a horizontal unit vector. And the real one we're interested in we're calling the collision angle, and it is the deviation from a perpendicular relationship of the force and velocity vectors. So if force and velocity are perpendicular, there's no projection of force on velocity, there's no mechanical power, there's no energy expended in that instant of interaction of the center mass with the environment. that makes intuitive sense, I hope. So these are just the calculations of those angles at each instant. And what I'll be reporting today are stride average values for these angles. So instead of using the lowercase, here we're using uppercase theta, lambda, and phi to represent the stride average force, velocity, and collision angles. And that's what I'll be reporting about the different gaits. We're really just two gaits, walking and running, of humans today. I just wanted to point out that force angle is averaged a summation of the magnitude of force, velocity by the summation of velocity, and collision by the summation of product of force and velocity magnitudes. So it's just a weighted average. So I've already mentioned the collision fraction. We can talk about the collision fraction at each instant, in which case it's just the instantaneous collision angle as a fraction of the sum of the force and velocity angles. So the collision angle represents what I've been calling the actual collision, and the sum of the force and velocity angles, which are perpendicular references, represents the potential for collision. So at any given instant, those the force and velocity vectors can be kept perpendicular, and we're not having any collisional loss. But if they're not, then we do have a sum. So as I said in the beginning, this approach doesn't make any assumptions about an inverted pendulum or a spring-loaded inverted pendulum, but I do want to point out that the zero collision case would an example of a point mass inverted pendulum with no step-to-step transition, something that doesn't exist, would be represented, would be an example of something with zero collision fraction. So no actual collision, but there would be a force and velocity angles that would be non-zero, so there'd be a potential collision. The compliant slip, so basically a springy leg running along. If it were sort of an idealized slip, which as I've mentioned, is sort of a cartoon drawn by Tom McMahon. That type of slip would have a collision fraction over the stride of 1. So those are sort of associations, but not necessarily tied to this approach, which is a general way to analyze any stride. So really quickly before I go on, I want to sort of suggest that it may be a sensible thing, more sensible sometimes than we think of when we think about the complexity of parts swinging around, and it may be more sensible than we think to go ahead and analyze the center of mass mechanics as a starting point. This is a study, a fairly old study by Rampositz, comparing, looking at mechanical power across speed. So the y-axis is mechanical power per kilogram, and speed is on the x-axis. And we can calculate out of that a cost of transport. This cost of transport came from center of mass approach. This one came from inverse dynamics approach, looking at the individual power of every joint. So as you see, they come out closer. In fact, for some reason, the approach looking at the joint powers gave a lower cost of transport in this analysis. So we think it's a reasonable a reasonable starting place to look at a center mass model. Our experiment considered only one speed of walking, rather slow walking, 1.1 meters per second, rather slow running as well, only 1.9 meters per second, and we used 4 force plates in a series, only 8 subjects, and we only took one trial of walking, 1 trial of running from each subject. So it's not a huge, for stats and things, it's not a huge study. This is just to give you a reality check what the data look like. These are accelerations, horizontal, already drawn, and the verticals are animated here. So this is, as most of you recognize, are a series of running steps with flight times between them, and you probably looked at these before. So when Tudor analyzed these, what he did was just highlight the steps and find and actually, the algorithm found the peak force, and we defined the stride as the time from peak force of the second to the fourth curve here. I think I have to hustle, actually. You know what walking looks like? That. And here are the results. So we considered, first considering the collision angle. Let me point out what's here real quick. We have force angle, velocity angle for walking, the same thing for running. And this is the collision angle, and then this is that collision fraction, which represents sort of the collision reduction, the level of collision reduction for that particular gait. So John Bertram would say the stats are in the bloody obvious category here. P is less than 0.001. You don't have to even look at the p-value. But the collision angle for walking is 0.08 and for running is 0.29. Collision fraction is 0.5 for walking. Fairly substantial collision reduction for walking, and not very much collision reduction for running, but it still doesn't look quite like an idealized slip either, which we think would be right around 1. So just won't spend any time on this, but just to convince you these things are real. These are the time-varying patterns of collision angle for running and collision angle for walking, and these are scaled to the same scale. So you see that the instantaneous collision angles are a lot smaller for walking than they are for running. And of course, you would probably recognize the force patterns in red in the background as well. This is a very early rough attempt, a failed attempt at wavelet analysis. It's basically a cry for help. If you have any, we want to do some sort of temporal analysis of the collision angle, and I'd love to talk to people if you have ideas about that. Don't tell John I said that. That it's a cry for help. But I want to. Do I have any minutes left? I have no minutes left. I want to sort of tell you that the collision angle is a very good proxy for cost of transport, and I've been collecting values for cost of transport. If you want to convince yourself of that last statement, it's in my paper last year, 2011 interface paper. But I tried to, from this meeting and from other sources, I was amazed that in human literature, nobody's reported mechanical cost of transport. I had to back calculate out of data like the Ramsden's data, where it showed mechanical power versus speed. And so that's a handy thing to do. This study, if we don't consider individual limbs, walking with individual limbs, Donnellan and others walking, so those agree nicely. Here's our running. We have here ostrich walking and running, fast running from ramposites of humans in green there. Some robots reported by Steve Collins and others in 2005, and I'm assuming the speed is low, 0.7-ish, less than 1, but I'm not really sure about that. These are everything at this meeting so far. Mechanical cost of transport has been 0.04, so that's Cornell Ranger, the Spring Flamingo down here in the black. And I believe that's the W prize, although I didn't really get my hands on firsthand on those data. So thank you for your attention. And
Okay, so while the next speakers start setting up, we have time for maybe 2 quick questions. Or maybe one long one.
Why did you choose that font?
The question was about the plot, right?
I don't know the answer to that one, I'm sorry. It just happened. Why is it not higher for running? I think it as you may have noticed, it was pretty high for trotting quadrupeds. It looked a lot, it was 0.93, 0.97. I think one reason might be this is really slow running. And I think that the sort of cartoon-like slip that would say that there's never any collision reduction probably doesn't account for things that happen during foot on and foot off and that sort of thing. And But I would be really interested to know, and at this meeting, several people have actually suggested that collision fraction might be a useful way to assess the slippiness of a runner, how slip-like a runner is. So I hadn't really thought about that. It was always
All right,